there. How are you? Thanks for stopping in. You know what jumping off a swing reminds me? Reminds me of kind of like I'm a tangent line leaping off of a curve. Same kind of feeling. We can do tangent lines and equations of tangent lines for lots of curves. But one thing we haven't looked at yet is what about circles? Tangent lines are really common in circles. How do you calculate the slope or the instantaneous rate of change when you're on a circle? It's all about implicit differentiation. Let's take a look at that next.
Let's take a look at this circle we have here. Notice it has a center at the origin and it has a radius of 5. So what would the equation of this circle be? Well, a circle with a radius of 5 consists of all of the points that are exactly 5 units away from the origin. So if we think of any point on the circle, we know that its distance is 5. Well, the x and y values form a triangle. In this particular case, our x value, of course, is -3, and our y value is 4. But for any point on the circle, no matter where it is, I can draw a similar triangle to that using x and y as my values. And since it's a right-angled triangle, in every single case, it'll be x squared plus y squared equals 5 squared. That's just from the Pythagorean theorem, c squared equals a squared plus b squared. So this equation for that circle is x squared plus y squared equals 25. In general, the equation of a circle is x squared plus y squared equals r squared. That's provided where r is the radius of the circle and the center of the circle is the origin. I'm just going to pull that up here. So obviously a circle has tangent lines. Let's just take a look at a couple of them. So there's a tangent line right here at the point 3, 4. Notice the slope of that tangent line is definitely going to be negative. Here's a really easy tangent line. There's a critical point here. Equation of that tangent line, of course, is y equals 5. It has a slope of 0. So there's one tangent line we know, and then, of course, there's other tangent lines as well. There's one with a positive slope down here. Okay, let's get back to how do we algebraically take the derivative of the equation of a circle so that we're able to find these instantaneous rates of change. Okay, well, one thing that we need to realize is the difference between equations that are defined implicitly and explicitly. So far in this course, we've been dealing with equations defined explicitly, clearly defined. They're written in the form y equals f of x. So the left side of the equation is either just a y, okay, or an f of x. You know, another one might be, it's meant to be a cubed root. F of x is the cubed root of x squared minus 1. So the left side of the equation is either y equals or f of x equals or something like that. As opposed to implicit equations, y is not given explicitly in terms of x. For example, the circle's equation, x squared plus y squared equals 25. Y to the power of 5 plus x squared y minus 2x squared equals -1. There's another implicit equation. There's no y equals. Equations like those may or may not be written explicitly, and often they're not functions. A circle is not a function. It is possible that we could find the derivative of the circle by rewriting its equation and solving for y. We could do that. However, it's not necessary to do that. In fact, after we learn a new algebraic technique for finding the derivative implicitly, implicit differentiation, we'll find that this original equation, x squared plus y squared equals 25, is just as easy to take the derivative. It's actually easier to take the derivative without needing to rearrange it like this. The other thing to think about is that often equations, implicit equations, it's not possible to solve for y. I don't believe with this second equation right here, I don't believe you can solve for y there. It's certainly not easy if you can, and it might even be essentially impossible. So let's take a look at implicit differentiation. So as an example, we could look at the circle, x squared plus y squared equals 25. And we could try to find the derivative of the circle and then use that to find the equation of the tangent to the circle at the point 3, 4, which was actually one of the tangent lines I showed you on the graph. One thing we're going to notice as we work on implicit differentiation is Leibniz notation is way more useful than prime notation. And part of that has to do with the idea that there's a y buried in the equation when it's defined implicitly. And we don't usually see f of x or g of x buried in equations. I mean, f of x wouldn't be appropriate in this case. It's not a function either. What I think I'll do is I'm actually going to show you how to find the derivative implicitly, and I'm going to explain why it works. So here's how I do it. If I take the derivative by taking the derivative of both sides of the equation, or differentiating both sides of the equation. When I do that to the right side, the derivative of 25 is 0, because it's just a constant. The derivative of x squared is 2x. Now, how do I take the derivative of y squared? I do it as if it's an x. And I get 2y, and then I multiply by dy by dx. And now I can solve 2y times dy by dx will equal negative 2x. Divide both sides by 2. dy by dx. Sorry, y times dy by dx equals negative x. dy by dx is equal to negative x divided by y. That is the formula for the derivative of a circle with a radius of 25. Actually, notice that the radius had nothing to do with our result. Okay, and that should make sense too. It doesn't matter how big your circle is. Your tangent line's slopes are going to be the same no matter how small or how big you make that circle. Notice that y is in the derivative as well. That shouldn't be a surprise either. Y was in the original equation, so it's natural that it would also appear in the derivative. Okay, well, at the point 3, 4, we could say dy by dx is equal to, well, we had negative x over y, so negative 3/4. Okay, and then, of course, finding the equation of the tangent, we can do that as well. Negative 3/4 will equal y minus 4 over x plus 3. And we can rearrange that however we want. Negative 3x minus 9 equals 4y take away 16. Or 3x plus 4y. Let's see, negative 16 and 9 will give you negative 7 equals 0. So there's our equation of the tangent line to the circle at the point 3, 4. Now, I showed you how to do that, and basically that procedure holds anytime you're doing implicit differentiation. But I didn't really explain what's going on, especially right here. I mean, the first step I did is I took the derivative of both sides of an equation. That shouldn't be difficult to understand. But why is the derivative of y squared 2y times dy by dx? Well, it actually has to do with the chain rule. Remember that when we looked at the chain rule, we talked about the idea that if x was input to u and u was input to y, then dy by dx is equal to dy by du times du by dx. Well, how does that apply when we have x squared plus y squared equals 25? And then we say 2x plus 2y times dy by dx equals 0. Well, what we actually have in this case now is we do kind of have these three different variables, if you will, or different functions within a function. X is input to y. You could think of it that way anyways. And then the outer function is actually y squared. So how do you take the derivative of y squared? You take the derivative of y squared with respect to y, and then you multiply by dy by dx. This is exactly what the chain rule tells you to do. So another way of looking at it is I'm actually doing this. I'm taking the derivative of y squared times dy, and then multiplying by dy by dx. Well, what does that give me? Well, that gives me the derivative of y squared with respect to x. So there we have this chain that works. dy squared by dx is dy squared by dy, and there's your 2y, times dy by dx. So let's just match that up. This right here corresponds to this value right here. And then, of course, this right here corresponds to this right here. And that's why it works. So here's a very similar example. X squared divided by 4 plus y squared equals 1. So let's use implicit differentiation. We take the derivative of both sides of the equation, and I get 2x over 4 plus, okay, the derivative of y squared is 2y times dy by dx equals the derivative of 1 is 0. Solving for dy by dx. Okay, notice that 2x over 4 is the same as a half x, so I get negative 1/2 x. Okay, don't forget that. So dy by dx, divide both sides by 2y, and I get negative x over 4y for my derivative. Now what does this curve look like? Let's talk about this next. Notice it's a lot like the unit circle. X squared plus y squared equals 1. However, we've taken x, instead of having x squared, we have x squared divided by 4. So it's actually like we took x and replaced it with a half x. Well, think back to what you know about transformations. If you replace x with a half x, it's actually going to horizontally stretch the graph by a factor of 2. Okay, because now you need bigger x values because the first thing you do is divide them by 2. So horizontal stretch factor 2 is going to give you this shape right here. You might want to call that an oval. Of course, mathematicians can't call things ovals. That's way too simple. It's an ellipse is the proper name for that shape. Sometimes implicit differentiation is easier even if the function is defined explicitly. So look at this one with y equals the cubed root of x squared plus 4. And we want to find the slope of the tangent at x equals 2. Well, first thing I could do is I could actually cube both sides of the equation. And I get y cubed equals x squared plus 4. And then, although I no longer have an implicit equation, I can still take the derivative implicitly. So I'll take the derivative of both sides. I get derivative of y cubed is 3y squared times dy by dx. The derivative of x squared is 2x, and of course the derivative of 4 is 0. So that means that dy by dx is equal to 2x divided by 3y squared. Now I want to know the derivative where x is equal to 2, so I have one of two choices here. Either I can take my y squared value here, and I can replace it with the cubed root of x squared plus 4. Or I can do this. I can just say, okay, at x equals 2, y is going to be equal to the cubed root of 2 squared plus 4, which is the cubed root of 8, which is also equal to 2. And dy by dx, we can now sub those values into our equation. 2 times 2 over 3 times 2 squared, which is, let's see, what is that? 4 over 12, or 1/3 for our answer. Let's look at a more difficult example, and this example is quite a bit more difficult. This equation can't be written explicitly, and it's quite a bit harder to find its derivative even with implicit differentiation. If you want a challenge, pause the video, try to do this yourself and see how you make out. Okay, let's take a look at it step by step. Taking the derivative of both sides, starting with y to the power of 5, we're going to get 5y to the power of 4 times dy by dx. Plus, okay, take a look at x squared y. That is technically a product. We are going to need the product rule to do this. So the derivative of x squared y is the derivative of x squared times y. So 2x times y, 2xy, plus x squared times the derivative of y. Well, the derivative of y, thankfully in this case, is just dy by dx. Think about that. The derivative of y with respect to y is just 1. times dy by dx. Or, hey, this is just regular differentiation. You take the derivative of the left side of an equation. If it's y, then you just write dy by dx. Subtract 4x equals 0. Okay, now we want to solve for dy by dx. So what I would do is I'm going to group my dy by dx's on the left side of the equation and everything else on the right side of the equation. So I get 4x, take away 2xy. Now I'm going to factor out the dy by dx. And then finally, to solve for dy by dx, I divide both sides of the equation by this value right here to get dy by dx is equal to 4x minus 2xy, all divided by 5y to the power of 4 plus x squared. Isn't that an ugly equation? But there it is. Now I'm okay with this derivative being an ugly equation because, to be honest, the original equation was pretty ugly. And it's certainly going to involve y's in it as well as x's. For fun, let's actually take a look at what this curve looks like. So here it is in Desmos. Notice you can type implicit equations into Desmos and it figures it out. So there it is, kind of interesting. Let's do one more example, and this one's going to be a very challenging one. Take a look at this mess of an equation. X squared plus y squared is equal to 5x take away x cubed y squared. Okay, and if I put that in Desmos, there's that rather odd-looking blob of a shape that it ends up making. How can we take the derivative of this and then actually solve for dy by dx? This one's a little bit challenging. To start with, on the left side, I'm going to think of kind of like my power of a function rule, which we now know is really just the chain rule. 2, so there's my power rule, okay, and then to the power 1, times the derivative of this stuff, which we now know is 2x plus 2y times dy by dx. Okay, equals, I'm starting a new line here, that can't be a good thing. The derivative of the right side of the equation. So it starts off with 5x, so the derivative of 5x is just 5. Subtract, I now have a product here. So the derivative of x cubed is 3x squared, and I times that by the second factor. And then I add x cubed times the derivative of y squared, which is 2y, times dy by dx. Now I've made one little mistake here. Notice I'm subtracting x cubed y squared. So when I take the derivative, I better include those brackets as well. Okay, now let's work on expanding this thing out. So starting with the left side, I'm going to expand here. I get, when I do that, so I multiply 2 by x squared and y squared. Let's just do that to start. And I'll take care of that negative as well on the right side. So I don't need those brackets anymore on the right side. Okay. Working on the left side, or the top line now, I'm going to use my distributive property, FOIL, to expand that. And when I do that, that's what I get. I've expanded all this line out using FOIL, and then I'm not going to do anything to the right side right now, so I'll just write it down below. And now I've got this ugly mess. I want all my dy by dx's on the left side of the equation and everything else on the right, so I'm just going to rewrite it like that. So when I put my 3 terms with dy by dx in them on the left, there's one there, 2, and there's another one there. Okay, of course that one becomes negative when it appears on the left side of the equation. And then that is going to be equal to everything else, and I have to move some of these terms over. So 5, take away 3x squared y squared, and then it's going to be take away 4x cubed and take away 4xy squared. And I've got 1, 2, 3, 4 terms taken on that side as well. Okay, so now what do I do to the left side? I factor out the dy by dx, and then I divide by what's left. So if you think about what that's going to look like, I'm going to have dy by dx is equal to 5 take away 3x squared y squared minus 4x cubed take away 4xy squared, all divided by what I would get here when I factor out the dy by dx, which is 4x squared y plus 4y cubed minus x cubed 2y. There it is. Well, normally I would write 2x cubed y, so let's just fix that to 2x cubed y. And there you have it. That's about as difficult as they're going to get. That ugly mess for your derivative there. All right, check out the homework questions I've got assigned, and there's some other resources to help you out as well if you're struggling with some of these problems, implicit differentiation. Look forward to talking to you later. Bye for now.